Today we are going to learn about deep learning approaches in time series forecasting. We will explore how deep learning models, especially LSTM and ConvLSTM networks, can revolutionize the way we forecast time series data. By the end of this video, you'll have practical skills to apply deep learning techniques for enhanced forecasting accuracy. In recent years, deep learning has transformed numerous fields, and time series forecasting is no exception. As data complexity increases, traditional methods struggle to capture the intricate patterns present in time series data. Deep learning models, such as long short-term memory, LSTM, networks, offer a powerful solution by effectively modeling nonlinear dependencies over time. In this video, we will delve into various deep learning approaches that enhance forecasting accuracy, adapt to complex data patterns, and lay the foundation for integrating advanced techniques such as attention mechanisms. Let's begin our journey into the world of deep learning for time series forecasting.
Deep learning models have become essential tools in time series forecasting, providing significant improvements over traditional methods. Traditional approaches, like ARIMA and exponential smoothing, often fall short when dealing with nonlinear and complex patterns. Deep learning models, particularly neural networks, excel in capturing such intricate patterns. These models are designed to handle sequential data, making them ideal for time series analysis. Their adaptability allows them to be applied to various types of time series data, whether univariate or multivariate. In this section, we will explore the fundamental concepts of deep learning as applied to time series, highlighting their advantages and setting the stage for more advanced techniques. Long short-term memory, LSTM, networks are a type of recurrent neural network, RNN, specifically designed to handle sequential data, making them highly suitable for time series forecasting. Unlike traditional RNNs, LSTMs can capture long-term dependencies by using a unique architecture that includes forget, input, and output gates. This design helps overcome the vanishing gradient problem, allowing LSTMs to maintain information over long sequences. They excel in tasks where context and order are crucial, such as language modeling and, of course, time series forecasting. In this section, we'll delve into the architecture of LSTM networks, explore how they function, and discuss their real-world applications in predicting time-dependent data. Setting up and training an LSTM model involves several key steps, starting with data preprocessing. Time series data often requires normalization and may need to be reshaped into sequences suitable for input into an LSTM model. Once data is prepared, the next step is to build the LSTM architecture. This involves defining the number of layers, neurons per layer, and activation functions. During training, hyperparameters such as learning rate, batch size, and number of epochs play a critical role in model performance. Evaluating the model involves splitting data into training and validation sets and using metrics like mean squared error, MSE, to assess accuracy. Fine-tuning the model by adjusting hyperparameters or using techniques like dropout can further enhance performance. In this section, we'll guide you through the process of setting up an LSTM model, training it effectively, and achieving optimal forecasting results. The ConvLSTM model is an innovative approach that combines the strengths of convolutional neural networks, CNNs, and long short-term memory, LSTM, networks, making it particularly effective for spatiotemporal data. By incorporating convolutional layers, ConvLSTM can capture both spatial and temporal dependencies within the data. This ability is especially valuable in applications like weather forecasting, where both spatial distribution and temporal patterns are crucial. In this section, we'll explore how ConvLSTM enhances feature extraction and improves forecasting accuracy by leveraging the combined power of CNNs and LSTMs. We'll also compare ConvLSTM to standard LSTM models, highlighting their differences and use cases.
Multivariate time series data presents unique challenges, as it involves multiple interdependent variables that need to be analyzed simultaneously. Traditional forecasting methods often struggle to model these complex relationships. Deep learning approaches, on the other hand, excel in handling multivariate data by capturing the intricate interdependencies between variables. Techniques such as multi-input LSTM models allow for the integration of multiple data sources, improving forecasting accuracy. In this section, we'll discuss the challenges of multivariate time series forecasting, explore deep learning techniques that address these challenges, and provide practical examples of how these models are applied in real-world scenarios.
Attention mechanisms have revolutionized deep learning by allowing models to focus on the most relevant parts of the input data, enhancing both interpretability and accuracy. In the context of time series forecasting, attention mechanisms help models prioritize important features and temporal patterns, leading to better predictions. When combined with LSTM networks, attention mechanisms enable the model to dynamically allocate focus across different time steps, capturing significant trends and anomalies. In this section, we'll introduce attention mechanisms, explore their role in improving forecasting accuracy, and demonstrate their application in time series analysis. By understanding how attention works, you'll be able to enhance your deep learning models for more precise and interpretable results.
To bring the concepts we've discussed to life, let's walk through a practical example using TensorFlow, one of the most popular deep learning frameworks. We'll start by setting up the TensorFlow environment and importing necessary libraries. Next, we'll implement an LSTM model tailored for time series forecasting. Using real-world data, we'll train and evaluate the model, focusing on key metrics to assess performance. Throughout the process, we'll discuss techniques for interpreting results and improving accuracy, ensuring you have a solid foundation to apply these skills in your projects. This hands-on example will provide a comprehensive understanding of how to build, train, and optimize an LSTM model in TensorFlow.
In this section, we'll explore a practical example using PyTorch, another widely used deep learning framework. We'll begin by setting up the PyTorch environment and importing the necessary libraries. Then, we'll implement an LSTM model specifically designed for time series forecasting. With real-world data, we'll train and evaluate our model, paying close attention to key performance metrics. We'll also explore PyTorch's unique features for optimizing model performance. This hands-on example will equip you with the skills to effectively use PyTorch for building, training, and optimizing LSTM models in time series forecasting applications.
Evaluating and fine-tuning deep learning models is a critical step in achieving high forecasting accuracy. Model evaluation involves assessing performance using key metrics such as mean squared error, MSE, and mean absolute error, MAE. These metrics provide insights into the model's predictive capabilities and identify areas for improvement. Fine-tuning techniques, such as adjusting hyperparameters, implementing regularization methods, and using dropout layers, help optimize model performance and address issues like overfitting and underfitting. Continuous improvement strategies, including cross-validation and learning rate adjustments, ensure the model remains robust over time. In this section, we'll delve into the importance of model evaluation, explore techniques for fine-tuning, and provide strategies for continuous improvement in deep learning-based time series forecasting. As we conclude this exploration of deep learning approaches in time series forecasting, it's clear that these advanced techniques are transforming the field. By capturing complex patterns and improving accuracy, deep learning models are setting new standards in forecasting. Looking ahead, the integration of emerging technologies such as reinforcement learning and unsupervised learning promises to further enhance these capabilities. We encourage you to continue exploring this exciting field, utilizing the resources and examples we've provided as a foundation for your learning journey. Thank you for joining us, and we wish you success in applying deep learning approaches to your time series forecasting projects.